Okay, good. Let me put this in. I wish it went full screen for that, but okay, cool. Okay, are we good?
Yes.
All right, hi everyone. Today we're going to be talking about testing for correlations between metallicity and the peak mass of the IMF, or initial mass function of a star-forming cluster. This paper was written by Morton Anderson and some people in Professor Tan's group. So the namesake of the paper is the IMF. I was going to put a Mission Impossible reference in there, but didn't have space. So over here on the left, we have like a cartoon IMF that I think everyone's seen in an intro class. And then over here, we have the one for scientists. The two IMFs that we care about are this purple one, which is the Chabrier IMF, and I can't pronounce it, Demarchi and Versace IMF. And we can see that both of them peak at around 0.2, 0.3 solar masses, and then that agrees with the cartoon. So ultimately, all of these shapes come from the manner in which a molecular cloud collapses and forms that cluster. We're primarily interested on these filaments and clumps that happen when we have turbulence that creates overdense regions, and then those collapse due to gravity. We can think about those like hydrostatic equilibrium in stellar astrophysics, where gravity is pushing in and then heat is pushing out, where heat is the gas being compressed and also gravitational potential being converted into heat. And that's where metallicity comes into play, because we don't really know exactly how that affects the IMF. Metallicity is simply the presence of substances that are heavier than hydrogen and helium, so that's going to have more quantum energy levels. So the presence of metals would mean that the gas gets the opportunity for its heat to be absorbed by these things, and then those electrons jump up and then come back down to ground state, and then they emit radiation. So ideally, metallicity means that there's less heat pressure because it's being emitted, which means that these clumps can get smaller, so the gene's radius is smaller, and then the gene's mass would be smaller, so that would favor lower mass stars. But then also, metallicity is dominated by dust grains, which would decrease the opacity. So it's kind of weird. Metallicity is going to increase the rate of radiation, but then also decrease it. So there might be a bit of a parabolic relationship there. Thankfully, those peaks, it's outside of the mass range that we're dealing with. So yeah, previous studies kind of, they can't really agree on the effects of metallicity. On the theory side, some simulations say that there's no correlation. Some say that there are. They don't really take into account magnetic field strength or stellar feedback. And then on the observational side, observations of the Large Magellanic Cloud only go down to 1 solar mass, which is way higher than the peak that we're interested in. And then galactic studies, well, they don't really vary in metallicity, so they're not very useful. But also, if that assumption that metallicity shifts the IMF towards the lower end is true, it's kind of a difficult endeavor up until now, just because lower mass stars are going to be dimmer, and they're also embedded in all sorts of stuff. So thankfully, JWST solves that. But then the other issue is we want low metallicity candidates, which are going to be hard to find in the galaxy. Usually when we want to probe low metallicity targets, we look at the Magellanic Clouds, but then those are far away, so dim stars, again, are harder to detect. And then also, you're going to have crowding effects, like stars might overlap with each other within any given pixel. Thankfully, that's where our cluster of interest comes into play. It's within the galaxy and uniquely low in metallicity. And then we also don't have to deal with the fact that it's too far away for us to detect M stars or brown dwarfs. And then also no crowding effects. So we move on to how they reduce the data. It's a multi-step process, just like our first project. They define a magnitude limit, so anything that's too dim they toss out. Anything that has too high of uncertainty they also toss out. Then they also compare it against a control field in the galactic plane. So they use that to separate out other galaxies and also foreground stars so that they can isolate cluster members. Then once they have the cluster members by themselves, they define an annulus based on a completeness limit. So they insert artificial stars and then run that pipeline and see if they can extract that star again, like recover it. And they find that down to like a certain limit. I believe it was 0.1 solar masses. That's where they can't really recover it anymore after CMD fitting. And then also for a similar reason, they also define a saturation limit of about 0.6 solar masses, just because above that it gets too bright for these photometric bands to be able to do anything useful. So then moving on to stellar fitting. It's our favorite CMD and isochrone. So they take those remaining stars and de-redden them to this solar metallicity isochrone. I'll get back to that. And then they'll use a geometric chi-squared sort of fitting and compare it against those isochrone points to estimate mass. Since they don't know exactly how old the cluster is, just that it's young, they do that for both a 1 megayear and 2 megayear isochrone. So we come here. This looks like a lot, but we'll walk through it. This column is for the 1 megayear isochrone fit. This column is for the 2 megayear isochrone fit. And then because they're doing it in color magnitude space, this one on the top, if you can't read that, they define the color band in the CMD to be 162 minus 182. And then the middle is 162 minus 200. And then the bottom is simply an average of the ones on top. So really we're interested in this one, which is our main scientific conclusion. It looks like the peak mass of the IMF is lower than the peak mass of galactic populations, but the result is suggestive and not at all conclusive, because if we come back here, if the age is actually 2 megayears, well, now we're kind of back in that 0.2 to 0.3 solar mass range, so highly sensitive to the assumed age. And then wrapping up with the limitations, there's a couple of things that need to be addressed in future studies if we want to make sure that this makes sense. The first one is, I don't know if you guys can see that, the dotted black curve is a solar metallicity isochrone, and the red curve is a low metallicity isochrone that would match our cluster. So I guess you guys can see that it doesn't go down into the brown dwarf range, which is not great. The low metallicity isochrone is just slightly bluer, but because they're so close, they simply chose to use the solar metallicity isochrone and simply accept the fact that there will be a systematic error. It's going to be a lot smaller than the photometric errors in the instrumentation, so it's just something that they can deal with. But obviously, if we want to be intellectually honest, yeah, we would probably want models that go all the way down. Secondly, stellar fitting is it's a pain in the ass. We don't know the exact age of the stars, and then there's also an age extinction degeneracy. Right here is a low mass star on the Barath isochrone, the 1 megayear Barath isochrone with 0.4 magnitudes of extinction in the KS band. But if we remove just a little bit of extinction and then make it 2 megayears, it still lies directly on the isochrone, but now it's a lot higher in mass than that one. So more work needs to be done on constraining extinction or mass, or both. And then finally, our cluster it's quite rare as a low metallicity, young, actively star forming inside the galaxy target. So there's 4 things on that checklist that have to be satisfied. So any future project would probably want to identify and observe similar clusters to try to confirm whether or not such a correlation actually exists. Okay, I'm 5 seconds away, so that's it. Thanks everyone for listening. If anyone has any questions, now's the time.
Perfectly on time. Questions?
Yeah, oh wait, should not point at you with the laser.
So the mentalist, so you mentioned a target with a low mentality and young. So it's in our galaxies?
Yeah, this is, that cluster is 4.5 kiloparsecs away from us, so inside of the galaxy.
So I was curious how, maybe I'm wrong, but I saw that all stars in the same galaxy should have the similar mentality, right? Or,
Wait, I don't think I understood your question.
You mean like you're surprised that this type of cluster has a low mentality?
Yeah. So it's not common, right?
Yeah, it's very uncommon.
But do you have any idea how they form? How they form this kind of?
I don't know. I assume that's the whole point of astronomy is figuring out how that happens. They have a good guess as to like its property is based on its spectroscopy of its cluster members. That they, within high confidence, assume that it's a young star, and it has an H2 region, so it's obviously actively star forming.
Well, let's talk about your project.
Okay.
Yeah. So, very interesting. What are you thinking about ways to extend this?
I would imagine the easy one is to simply write a proposal that, I don't know what I'm going to right now, but write a proposal that observes a cluster that's similar to S284.
Sure.
I'm not much of an observationalist, so I might be biased, but I think the better use of labor is to, I don't know, write some simulations or something that would extend those isochrone models. But that's also like what my own research is, so I'm definitely very biased there.
No, I think that's a fair question, right? And I should say, I'm open, I'm flexible as to the nature of the proposal, right? Like there's many different types of proposals at this point. Not all of them involve getting new data. And there's definitely theory, the whole theoretical landscape to explore as well. I think I would want you to think about, where is best time actually spent, right? How do we actually push the field forward? That's a really good way of thinking about it.
Well, I would imagine that observations that would confirm such a extension in isochrone models would be difficult, because I don't believe it's going to be hard to detect brown dwarfs in other galaxies.
Yeah, but how tractable is the simulation side?
That I'm not sure about.
Yeah. But so you're thinking, should you be working on extending the isochrons? But how would you do
that is one way to go about it.
But how would you do that in practice? What's your current setup?
See, that I'm not sure about, just because those models don't exist.
Yeah, that's
so.
the thing. The models don't exist, so I think that is, almost like a PhD project.
Yeah, that would involve simulating atmospheres and stuff. Yeah.
And there's very few groups that do it, so you have to sort of embed yourself within one of those groups, unless there's someone in Tan's group that is thinking about these things. So I think that would be outside the scope
Mhm.
of
Yeah.
the class a little bit. There is, yeah, and as you said, this is a, rare type of object. But yeah, I mean, an easy-ish path would be to identify other such objects using existing data and proposing the same thing.
Mhm.
But I invite you to think about where you think the actual data is.
Okay.
This is